Hey, welcome to the Shape of Intelligence. Now, in this first explainer, we are diving headfirst into a really provocative question that's at the heart of a whole new research program. And look, while this is part one of a larger series, don't worry, it's a complete story all on its own. You can jump in right here.
Okay, so let's just get right to the big idea. What if the reason AI is getting so incredibly expensive and just power-hungry isn't because we need more and bigger computers? What if it's because we've been using the wrong kind of math, the wrong geometry, this whole time? I know, it sounds a little out there, but it's an idea with absolutely massive, real-world consequences.
Let's start with why this even matters. Because, the way we're currently building AI, it's hitting a wall. A very real, very physical wall. The cost is just becoming unsustainable.
Okay, so get this number, 945 terawatt hours. That's what the International Energy Agency projects data centers will be eating up in electricity by 2030. Now, to wrap your head around that, that is more energy than the entire country of Japan uses today. This isn't some far-off future problem. It is happening right now. And this cost, it's not just about the electricity bill. It's so much bigger than that. First, you've got the raw energy crisis. I mean, training just one of these huge models can use enough electricity to power over 100 homes for a whole year. Then there's the hardware explosion. The demand for these super specialized, super expensive chips is just skyrocketing. But here's the part that really gets me. Most of that energy isn't even spent on the actual calculations, the thinking. It's spent just moving data around. And all of this together, it creates this massive centralization problem, where only a handful of giant companies can even afford to play at the cutting edge.
So, the research program we're talking about today suggests a totally different way of looking at this. It says, what if the problem isn't about scale, just making things bigger and bigger? What if it's a problem of shape, the actual geometry AI uses to organize information? Okay, let's really dive into what that means.
So geometry, right? Where does that fit in? Well, right now, pretty much every AI model out there organizes what it knows using something called Euclidean space. Don't let the name scare you. It's just the simple, flat geometry we all learned in school. Think of a grid on a piece of paper. It feels totally normal, totally intuitive. But it has this huge hidden flaw when you try to use it for the kind of complex, tree-like information that makes up our world.
And this is honestly the perfect analogy. Using that flat Euclidean geometry for complex information is exactly like trying to draw a map of the world on a flat piece of paper. Yeah, you can do it, but you get all those weird distortions, right? Greenland looks bigger than Africa, everything at the poles gets stretched out. To add more detail without it getting all wonky, your map has to get huge. But what's the better way? A globe, a curved surface. It just naturally captures how everything is related and how far apart things are.
So what's the AI version of a globe? Well, it's this really cool thing called hyperbolic space. Now, instead of being curved like a ball, the best way to picture it is kind of like a saddle. It curves away from you in every direction. And here's the magic trick. As you move away from the center, the amount of space available grows exponentially. It just explodes outward. And it turns out that structure is a perfect match for how tons of stuff in the real world is organized. Think about a family tree, or a company's org chart, or even the tree of life in biology. They all branch out and out and out. This geometry is just a natural fit.
Okay, so to really test this whole idea, the scientists didn't just write one paper. They built a complete integrated research program called Hyperbolic Geometric Intelligence. It's all about investigating this geometric idea in a really structured, really scientific way.
And what's cool is how the whole program tells a single coherent story, step by step. Step one is just about feasibility. They asked, hey, can we even do this? Can we take an existing AI model and squeeze it into this new geometry? That's the first paper. Then you move to step two, rigor. What's the exact math here? Which version of it works best? Then you get to step three, the vision. What would an AI that was born in this space look like? And finally, step four, the consequences. Okay, let's say this all works. What does it actually change for us in the real world?
And the results from that first feasibility study, the CGT paper, are, well, they're pretty eye-opening. Now, these are preliminary, but just look at this. They took a standard AI's knowledge representation, which was sitting in 768 dimensions. Think of dimensions as just different features it tracks. And they compressed it all the way down to just 32. That is a 24 times reduction. And the crazy part? It still kept over 97% of its ability to understand how different words and concepts relate to each other. That's huge.
But hey, this is science, right? One exciting result isn't enough. You need to know why it works. That's where the next part of the program, the Lorentzian family, comes in. This was a super systematic study where they tested 5 different mathematical models, from the simplest to the most complex. The goal wasn't just to find one magic formula. It was to really isolate what parts of the geometry were doing the heavy lifting and understand all the trade-offs. It's all about building that solid theoretical foundation.
Now we get to the really forward-looking part of the program, the H-LLM Specification. And I need to be super clear here. This is not a working AI model. It's a blueprint. It's a complete theoretical design for what a large language model would look like if it was born in hyperbolic space, if it learned everything from scratch inside this curved geometry, instead of just being moved into it later. It's definitely speculative, but it's an incredibly ambitious peek at a totally different way to build AI.
Okay, beyond all the cool results and the future vision, there's something else about this program that, for me, is maybe the most important part. It's the commitment to intellectual honesty. This entire research program was designed from the ground up to be proven wrong.
This quote from one of the papers really says it all. Basically, what it's saying is that it's not good enough for a model to just get a high score on some test. If the model gets that high score by cheating, by not actually following the rules of the geometry it's supposed to be in, then the researchers consider that result a failure. They call it a degenerate solution. It's about being right for the right reasons.
So to enforce that philosophy, they built in these 3 checks. You can think of them like a quality control system designed to catch the model if it's faking it. The first one, F1, basically asks, are the data points actually on the curved surface where they're supposed to be? F2 asks, is the sense of what's close and what's far still the same after you compress everything? And F3 is about neighbors. Are the closest concepts to any given point still its closest concepts in the new space? If a model fails these tests, it's out, even if its performance looks great.
And to top it all off, in the true spirit of open science, there are no black boxes here. Everything, all the code, all the experiment setups, all the data, is available for anyone to see on GitHub. That means you, or any researcher in the world, can go in, check their work, criticize it, and even build on top of it.
So, where does all this leave us? Well, if this whole geometric idea holds up, the implications are, well, they're huge. It brings us right back to those massive problems we talked about at the very beginning. Why does this matter? Well, for starters, efficiency. We're talking about the potential for dramatic drops in AI's costs and energy use. And what does that lead to? Accessibility. It could lower the barrier to entry, so it's not just a few giant companies who can afford to build powerful AI. All of this points toward a more sustainable path for the entire AI ecosystem. But maybe the biggest thing is this. It gives us a fundamentally new lens, a whole new way to even think about what intelligence is and how to build it.
And look, we are just scratching the surface here. This explainer is just part 1 of our series, The Shape of Intelligence. In the other parts, we're going to dig way deeper into what all this means for energy, for the economy, for society, and yeah, we're also going to talk about the risks and the big questions we don't have answers to yet. So when you boil it all down, this whole research program leaves us with one huge, exciting question to think about. Have we been trying to build our AI on a flat map this whole time? And is it maybe time we started asking, what is the true shape of intelligence?
And like I said, you don't have to just take my word for any of this. If you're curious, if you want to dig in and see for yourself, the entire program, every paper, all the code, the experiments, it's all open source. You can find it at the link you see right here. Thanks so much for joining me for this deep dive.